Today, we're going to test out what we've learned about the motion of projectiles in physics with real thrown objects. Will their predictions about their flight be accurate? Let's find out. The first thing that physics says about projectile motion is that it always follows the path of a parabola, something like this. This means that there's a peak at the top, and on either side, the parabola is symmetrical. Not only that, but it is perfectly upright.
But surely that may not be exactly right, isn't it? Isn't it possible that you could have thrown it lopsided or in a non-parabolic path? Here, the ball is thrown at different angles. We can see that these are all parabolas, even though they have different heights and ranges.
Note that this doesn't cover things like air resistance and properties that things like frisbees and boomerangs have.
Now, another thing that the math tells us is that at equal amounts of time before and after the ball reaches the peak, the ball is the same height above ground. In other words, getting from here to here should take the same time as getting from here to here. We'll test this by getting the exact time in number of frames.
The time it takes for the ball to reach the peak from the launch is 131 frames. Another 131 frames after that, and it returns to a height that is the same as when it was launched. Now, here's an interesting fact. Supposedly, you can separate the up and down vertical motion and the side-to-side horizontal motion of the projectile in flight. Since there's only one force acting on the ball, the force of gravity, which is downwards, then there should be a change in speed only in the up and down direction. For the side-to-side direction, the speed should be constant. Is this true? Let's test this by taking snapshots at regular intervals and looking at the distance the ball has traveled in between them. If the spaces are even, then the speed is constant. But if they are different, then some acceleration has occurred. Now, I'll line up the movement of the ball so it's the same height the whole time. Roughly speaking, the distances are even, indicating constant motion. However, in the y-axis, we see the spaces get smaller and smaller as they reach the peak, meaning it's slowing down, and get larger and larger after the peak, meaning it's speeding up.
Interestingly, at the highest point, the velocity is zero. If you think about it, to move in the exact opposite direction, you need to slow down to stop for a moment before reversing.
Personally, what I found most interesting about this whole exercise was the idea that even though the ball was slowing down and speeding up as it moved up and down, the side-to-side motion remained constant. I guess it shows us that even though there are some things in the world that are always changing, there are some things which remain the same. Anyway, that's all for now, and I hope that you learned something today.